In this example, we will study permutations with repetitions allowed. In Part A, there are 3 switches on an electrical panel. How many unique up and down sequences are there? Before we solve this, let's look at a few examples. One possible arrangement is up, down, up. Another possible arrangement is down, down, down. We know that there are 3 switches, and each switch can be up or down, but we don't know exactly how many switches are up or down. We can solve this by setting up positions and filling in the number of options. Use permutation tiles to represent the up and down states. There are 2 options for the first switch, up or down. Select a tile and continue. Each switch can be up or down, so carry forward, or in other words repeat, both permutation tiles. There are 2 options for the second switch, up or down. And there are 2 options for the third switch, up or down. Multiply the numbers to get 8. There are 8 unique ways the switches can be arranged. This is a single-case permutation because we have only one term. 2 times 2 times 2 is considered one term because there is no adding or subtracting. Now we'll take a moment to explore this question in more depth and compare it to other questions we have already completed. When repetitions are not allowed, we have a finite set of objects in our sample set, and availability decreases as positions are filled. For example, how many unique words can be formed from the 3 letter tiles S, E, E? In our sample set, we have the letters S, E, and E. Set up positions and use permutation tiles to represent the letters. There are 3 options available for the first position. There are 2 options available for the second position. And there is 1 option available for the third position. Rearrangements are possible, so we have to divide out the repetitions. The answer is 3 factorial over 2 factorial equals 3. There are 3 unique arrangements. When repetitions are allowed, we have sets of infinite objects in our sample set, and availability remains constant as positions are filled. For example, there are 3 switches on an electrical panel. How many unique up and down sequences are there? In the sample set, use the infinite symbol to show that up and down is unlimited. Now set up positions for switch 1, switch 2, and switch 3. When we are drawing from an infinite sample set, we may not rearrange the objects once they have been positioned. Use a lock icon to show that rearranging is not permitted. Use permutation tiles for up and down. There are 2 options for the first switch, up or down. The tiles are unlimited, so carry both forward. There are two options for the second switch, up or down. The tiles are unlimited, so carry both forward. There are two options for the third switch, up or down. Rearrangements are not possible because the positions are locked, so there are no repetitions to divide out. Multiply the numbers to get the answer. 2 times 2 times 2 equals 8. Now we'll move on to part B. How many two-letter words can be created using the letters A, B, C, and D? The quantity of letters has not been specified, so we can use each letter an unlimited number of times. Set up positions for a two-letter word. We are drawing from an infinite set, so the positions are locked and duplicate arrangements will not be formed. In this context, locking is just a fancy way of saying, if we select the letter A for the first position, then it's fixed in that position for the remainder of the question. So even if the second letter also happens to be A, we don't need to worry about dividing out repetitions since each letter is fixed in place and duplicate words don't get formed. Use permutation tiles to represent the 4 letters that are available. There are 4 options available for the first letter. There are infinite letters available, so carry forward all of the tiles. Even if we use up A, we can always pull another A from the sample set since A's are infinite. There are 4 options available for the second letter. Multiply the numbers to get the answer, 16. Since the positions are locked, rearrangements can't happen and duplicate words don't form. Therefore, we don't need to divide out repetitions. Now we'll move on to part C. A coat hanger has 4 knobs, and each knob can be painted any color. If 6 different colors of paint are available, how many ways can the knobs be painted? For this example, let's select paint colors of blue, green, orange, pink, red, and yellow. One possible way to paint the knobs is blue, green, red, red. Another possible way is red, yellow, orange, yellow. In both cases, we are making a 4-letter word out of the available letters B, G, O, P, R, and Y. No color quantity was specified, so we can assume each paint color can be used an unlimited number of times. Set up positions for each knob. Rearrangements are not possible, so lock each position. There are 6 colors available for knob 1. We can use each color an unlimited number of times, so carry forward all of the colors. There are 6 colors available for knob 2. There are 6 colors available for knob 3. And there are 6 colors available for knob 4. Multiply the numbers together to get the answer. 6 raised to the power of 4 equals 1296. We are drawing from an infinite set, so the positions are locked and duplicate arrangements will not be formed. Now we'll move on to Part D. A phone number in British Columbia consists of one of four area codes, 236, 250, 604, and 778, followed by a 7-digit number that cannot begin with a 0 or 1. The sample set contains 4 area codes and an infinite supply of digits. Set up positions for the area code and phone number digits. Lock the digit positions because we are drawing from an infinite set. Rearrangements are not possible, so duplicate phone numbers will not be formed. The area code position is not locked because the set of area codes is finite. Note that since there's only one area code position, locking or unlocking makes no difference. Use permutation tiles to represent the 4 area codes. There are 4 options. Now use permutation tiles to represent the 10 available digits. The first digit must not be 0 or 1, so 8 digits are available. This restriction is called a constraint. The constraint is removed for the second digit. We can use each digit an unlimited number of times, so carry forward all of the tiles to get 10 options for digit 2. There are 10 options available for each of the remaining positions. Multiply all of the numbers together to get the number of unique arrangements, 32 times 10 to the power of 6. Now we'll move on to Part E. An identification code consists of any 2 letters followed by any 3 digits. How many identification codes can be created? The sample set contains an infinite supply of letters and digits. Set up positions for the letters and digits. Lock the positions because we are drawing from infinite sets. Rearrangements are not possible, so duplicate identification codes will not be formed. There are 26 letters available for the first letter. We can use each letter an unlimited number of times, so there are still 26 options for the second letter. There are 10 digits available for the first digit position. We can use each digit an unlimited number of times, so there are still 10 options for the second digit. There are 10 digits available for the third digit position. Multiply the numbers together to get the number of unique identification codes, 676,000.